The next batch of circuits we're going to look at are all designed to control the rate of flow, right? So keep in mind for pneumatic systems, we generally control the rate of compressed air because it controls your actuator speed, meaning how fast your cylinder is going to extend or retract or how fast your motor is going to rotate. As we talked about earlier, we have essentially two options in pneumatics: metering in and metering out. Metering in controls the flow rate in, metering out controls the flow rate out. And if you recall, metered out circuits generally are preferred because they prevent any type of self-actualizing due to positive loads, right? So in our case here, particularly when we're dealing with compressible air, we want to control the flow rate out so we get more stable actuator movement, right? So it's smoother, it's not jumpy, it's not sudden, etc. To do this, we need to put a flow control valve, and keep in mind we want to keep it pretty close to the actuator. Anytime you put a distance in, that's a chunk of air that is compressible, so essentially can act like a spring. So by keeping the valves very close to the actuator, you have less of that springiness due to the compressibility of fluid. So the simplest of the example of this is a single acting cylinder that we want to be able to control the speed of extension and retraction. So here we have our system, right? Airflow coming in, our FRL unit comes to a three-way directional control valve. Here's an exhaust with a muffler on it. If in a normal position, it would actually be draining the air out. Once you push this button, air goes through. Obviously, this check valve is going to stop the air from coming this way. It comes down here, and it pops this open, flows in, and extends it. Right. On the other hand, when we move this to the opposite direction, go back to its normal position, we then vent the air out. Right. This is not going to let air flow in this direction because that check valve is going to block it. On the other hand, it is going to allow air. So in this way here, valve A can be used to control the extension rate, and valve B can be used to control the retraction rate. Right. So in this case, we are metering the flow. This one actually is metering the flow in. This is actually metering the flow out. So this would generally be used if we know we have a positive load. So for example, this one is shown vertically, probably a pneumatic ram where there is a constant load in here. So there's always going to be a positive pressure on this. The common device used for this type of thing is a needle valve, and you'll notice that this has this dashed dot line around to show that the check valve and needle valve are both in the same housing. So this would be what was referred to as an integral check valve. The next more complicated circuit we're going to look at is if we wanted to control the extension and retraction of a double acting cylinder. So to do this, we're going to need a four-way valve. Right, this is a four-way directional control valve, and of course we need that additional port because we want to send fluid to extend the cylinder. We're going to send it to the blind side. To retract the cylinder, we're going to send it to the rod side. Right, so in this case here, the cylinder is fully retracted in its normal position. We would actuate the valve by pushing this manual control. The fluid's going to come out here, right? In this case, high pressure air gets to here. Notice our flow control valve is a little bit different. All right, this is got flow control, but it has a built-in bypass, right? So this check valve allows it to bypass. So in this case, it allows free flow during extension, right? So the check valve pops open and the fluid will flow right through here. So this will start to extend. This will push air out of the rod side. When it gets here, notice the check valve prevents flow in this case and forces it through the flow control valve. Right. Keep in mind, flow control valves do have a certain amount of resistance. They're, a restricted orifice of some type, probably a needle valve. And so this is going to meter the flow out, metered outflow during extension back here and out. On the other hand, if once the full cylinder fully extends, we want to retract it, we would release this. It moves back to its main position. That's what the spring's going to do. High pressure fluid is going to come out this side. It's going to get to here. This bypass is going to open. That's going to allow it to start retracting. Of course, the flow coming out of here. This valve does not allow it to bypass in this direction, so we control the flow. So now we're metering it out during retraction. And this is going to give us much smoother motion. And the reason behind that is because there's always going to be a certain level of pressure on the piston that has to be overcome. So the circuit has to move more smoothly and more stably. We can accomplish the same thing with a 5-port valve, right? Essentially, we're doing the same thing, but we're placing our flow control valves here, right? So when we want to extend the cylinder, we would actuate this valve, right? Fluid would come out and extend it, and we are going to meter the flow out because it's going to come back here and go through valve A. On the other hand, when we retract it, high pressure fluid is going to come out this side, go through here, come back, and it's going to go out through valve B. So by adjusting valve A and valve B, we can control the flow. Right, so the flow rate, which is going to control the speed. And again, there's a certain amount of back pressure because it does have to be pushed through these flow control valves. In this circuit, we have a situation where we want our cylinder to be able to extend at 2 different rates. This often occurs in a manufacturing environment where you want to bring the tool up close to the part and then do some type of operation, oftentimes a machining operation, at a much slower speed. So we want to get the tool there quickly. It's referred to as a rapid advance, but then have a lower speed to actually do the function that you want to accomplish it. In this case, to get those 2 different speeds, we need 2 different airflow rates. So our setup here, if you take a look at the circuit, we have our FRL unit, bring air in. It's normally set up so the cylinder is held retracted by the normal position of the valve, but if we manually activate it, the airflow is going to come from here and start to extend this cylinder. Now, in this case, the air comes out of here, right? The bypass valve isn't going to do anything because it's closed off. This is going to be restricted, but we have free flow through this valve, right? It's normally open, boom, out here, and eventually it's going to go through valve A. Valve A actually controls the starting extension speed of the circuit, and it meters it out. At a certain point, this cam surface is going to interact with this control, and it's going to actuate this valve and push it to the closed position. So at this point, once it gets this point here, the fluid can't flow through here any longer, the air can't flow through here any longer, and it's going to be forced through this flow control valve. Right, so this is going to have to be at a slower rate. It's going to reduce the flow. So our cylinder will extend quickly and then hit this point. When it hits this point, it'll then move more slowly. Now, on the return line, or on the retraction line, we would let this cylinder go back to its normal position. Airflow comes through, pops this bypass valve, goes into the rod side, and air coming out here would have to go through valve C and out. So valve C actually controls the retraction speed. Now, keep in mind, these could be manually operated. We could also put a solenoid valve, right, to control this. Or for that matter, we could actually connect this with pilot pressure and actuate it from a remote location. So far, we've been discussing relatively simple actuator motion control, essentially just extending and retracting cylinders. But keep in mind, particularly with automated pneumatic systems, we want to be able to control the motion functions in a more complex way. Oftentimes, we may want to do a series of motions or motions that are going to be linked to each other in some way. So the next group of circuits we're going to look at are designed to produce multiple movements somewhat automatically. So in this circuit, we want a double acting cylinder to extend, and once it reaches its full extension, we want it to automatically retract, right? Automatically return, essentially. So if you take a look, we have a 3-way valve with manual control, right? Our fluid comes in, our operator pushes this valve, depresses this valve, and this pushes fluid into this pilot line. This pilot line causes valve B to actuate, right? Slides over to this position. This directs fluid to our blind side and is going to extend our cylinder, right? So extends our cylinder. Eventually, this cam surface is going to hit valve C and it's going to change the position, right? In its unactuated position, the pilot line is vented. In its actuated position, the pilot line receives pressure. This is going to push the valve back and cause the cylinder to retract, right? So it'll automatically extend, and once the button's pushed, and then automatically retract. It'll stay in that position. It's held in that position until the operator pushes this again. Right, so you can think of a number of manufacturing applications, presses and punches and things like that, even drills, where you'd want it to move forward, do something, and then move back, and then wait for the operator to activate it again. So in this circuit, we want the cylinder to extend, retract, essentially continuously. Right? We want it to have reciprocating motion. And essentially we're using two sets of the controls we had in the previous one. The operator would initiate the process by depressing valve A, right? So fluid is going to be directed into the circuit. It's going to come out here. It's going to start the cylinder retracting. If the cylinder is completely retracted, which is probably how it is, the cylinder starts up, that opens valve B. Valve B then sends pilot pressure over here and pushes the, in this case, our 5-way directional control valve over. That sends fluid through this flow control valve and extends it. Right? Extends out. Eventually, this cam surface hits valve C when it gets to full extension. This pushes this down, sends pressure over here. This is the retraction pilot, right? And that slides the valve back over and starts the whole process all over again. Right? So essentially, this will keep extending fully, retracting fully until valve A is released. And at that point, the device will stop. Now let's take a look at a few circuits that are designed to do a specific function. For example, this is what's known as a booster circuit. And this is when we have a situation where we need high pressure for some limited aspect of our workstation function. So it might be something to hold something or associated with some sort of press or something like that. And it wouldn't be economical to run the entire pneumatic system at this elevated pressure. Or an alternative would be to put in a secondary pneumatic system that operates at high pressure. Both of those are pretty costly. This is a relatively inexpensive way to accomplish the same task. And what it does is it intensifies the pressure or increases the pressure. So it can do this by creating high pressure air, or it can also be used to actually produce high pressure oil. And keep in mind, we oftentimes want to use an air to oil booster because of the fact that we generally prefer oil when we have higher pressure applications due to that issue of compressibility. Now, this is going to be limited to relatively small volumes. If you really needed a high volume of high pressure air or high pressure oil, you probably would need an alternative system. But as long as the volume is relatively low, this system works out pretty nicely. So if we take a look at our system here, we have our air line coming in, going through our FRL unit. And if you take a look, air is going to come in to each of these systems, right? Air is going to be, in this case, through valve A with the, we're going to activate this pressure, right? It's going to come over here and it's going to hold this circuit, right? When it holds the circuit in this position, this fluid is going to come to the, I can't really use the term blind side and rod side here because you'll notice this is actually a double rodded cylinder. right? This is one of the few places in the course we're going to see one of these used. This is when we have, it's a double acting cylinder, but it actually has a rod extending out of one side that's used actually for pressure, but it has another rod extending out of the opposite side, which is actually going to be used for control. Right, so when the fluid comes in here, and this gets the high pressure air, it's going to force the cylinder to extend. When the cylinder extends, it's going to push fluid out of this side and out of this exhaust. What this does, you'll notice this has a very large area. This has a relatively small area. The two different areas are clearly different, but the force that's being generated is the same, right? So large area, relatively low pressure, small area, much higher pressure, right? So the fluid gets pushed out, right? And this gets pushed into valve D. And obviously this is going to be higher pressure fluid. We also usually keep some form of accumulator here to actually hold the fluid, because keep in mind, this is not going to be, it's not going to be smooth, right? It's only going to happen when the fluid extends. When the fluid track, that's not going to give you the same high pressure. So we use this accumulator here, or a receiver. You can also refer to it as a receiver, to actually keep the fluid at a stable higher pressure and give more stable operation. Obviously, this control rod is going to control the reciprocation, right? Just like we talked about in the last one, where when it gets to the end of its retraction stroke, that opens valve A, causing it to extend. When it gets to the end of its extension stroke, it actuates valve B, causing it to return. And again, we're going to get that reciprocating motion back and forth and back and forth. This doesn't have any control on it, so this would essentially work anytime the system is pressurized. Now, this is a relatively small chamber here. Essentially, it's referred to as a air-powered pump. A reciprocating pump, essentially one piston to produce that fluid, right? Obviously, it needs to refill, right? So it's set up so it pumps out, gets refilled, booster goes out here, gets refilled, etc. So this is a simple booster circuit. If it was an oil system, obviously the refill would not come from the pneumatic line. It would come from an oil reservoir, and eventually you have to be sent back to an oil reservoir when it's done with the high pressure application. Here's another example of a special function circuit. This is if we want very fast extension and retraction. So we want to minimize any delays and maximize the operating speed. And the way we do this is we actually move our valves very close to the cylinder. Right, so the venting itself, the exhaust is very close as well, and it goes directly out to it. So this is set up so when this is set to extend, it actuates here, right? So in this case here, it's set to be fully retracted. Once we move it to extends, fluid's going to come out here. That's going to push it over to here and dump the fluid. So the fluid doesn't have to go back. The air doesn't have to go all the way back to be dumped. And vice versa, when we're extending it, the air can go directly out as well. So this gives us a much shorter distance for the air to travel and really minimizes the amount of pressure that's going to be required. Gives us a little bit more efficient operation, but there is some issues potentially with instability, because we don't have a huge amount of control in terms of metering the fluid out. It comes out pretty easily, so there could be some unstable behavior, but it will move very quickly. Another type of function that pneumatic circuits can perform is what's known as a logic function. This essentially is something we normally think of with computer controls, but you can accomplish the same thing with mechanical devices to a certain extent. Today, we're mostly going to use small microprocessors or PLCs to accomplish things like AND, OR, and NOR. If you're not familiar with these, essentially AND requires two inputs, so both A and B, that would activate the system, or essentially allows A or B, either one of them would activate the system. And NOR essentially means not or, so essentially means it can't be A it can't be A or B. So if neither of them are activated, the function will work. So these are the common types of logic. And in all honesty, we're not going to go into a lot of detail on these, but I wanted to just show you them so you'd be aware of it. If you go into electrical work, or if you go into industrial automation, these will go into a lot more detail. Now, as I said, this can be accomplished by computers, but we can also do this with relatively small and simple pneumatic devices. And essentially, we're using airflow and the pressure and sensing those flows to control the function. Keep in mind that a lot of these circuits were designed prior to the availability of microprocessors or computers in general. So we did want to accomplish this function prior to this, and we could do that just with pneumatics. So this memory circuit is an example of this. This is if we want to be able to keep a system functioning until we shut it off, right? And the way this works is if we start with valve A right here, so fluid comes on, this is normally closed. The operator would start the function by pushing this in. This is going to move over here, and it's going to, the pressure is going to make sure this shuttle valve is pushed to this position. If you recall, a shuttle valve essentially switches between two inlets, and essentially whichever is the higher pressure is the inlet that's going to function. Right, so in this case here, the high pressure fluid would come in and it would push this one. This pushes flow over here and opens the circuit, right, and essentially allows the fluid to go out to whatever function we want it to do. This is going to stay that way until someone comes along and hits valve B and stops it. At that point, this is going to slide over to this other position, right? It's going to slide over and essentially this is going to decrease the pressure on this side. This is going to send the shuttle valve back over to this side, and this is going to close this valve off, right? So essentially, this is a memory function where it's looking for either A or B, depending on what you want it to accomplish. Another example of using pneumatic devices to automate a system is these time delay circuits. So these actually use a pair of timing reservoirs and a pair of flow control valves to actually control which cylinder will extend first and in terms of the timing of them. So in this case here, the operator would actuate valve A, fluid would come in. In this case here, there would be resistance because it has to go through a flow control valve. On this side, on the other hand, we have the bypass. This would pop the bypass. Fluid would flow in here and allow cylinder 1 to extend, right? Once cylinder 1 fully extends, the pressure would go up, right? And the only path for the fluid to go through would be to go through cylinder 2. It would first have to fill this timing reservoir, however. So it would fill this timing reservoir. That would take a certain amount of time. Then cylinder 2 would extend. Similarly, when cylinder 2 was retracted, before cylinder 1 retracts, it would have to fill this timing reservoir before it popped the bypass valve and allow fluid to flow through. So using relatively simple devices, you can control these delays. In fact, you can vary the size of the timing reservoirs and vary the flow rate through these needle valves that will actually set the length of the delay, and you can adjust these. And keep in mind, these do have to be checked over time because wear and tear on the devices is going to change them to a certain amount. Now, lastly, I will say that in most modern equipment, a lot of this is controlled by microprocessors and PLCs, which actually have built-in timing circuits that should be a little bit more stable and something that definitely can be monitored. This, on the other hand, requires more active monitoring. The last of the circuits we're going to look at is known as a safety circuit. This is another example of one of those two-handed safety circuits that we discussed in hydraulics. The idea is with a variety of different manufacturing equipment, we want to keep the operator's hands away from any of the functions. So we set up a pair of valves in here that have push buttons that have to be manually depressed. Until both valve A and valve B are depressed, the cylinder is not going to move over here. And the whole idea of this is to make sure that your hands are clear and prevent any type of machine operation which could hurt you or damage your hands in any way. So you essentially have to keep your hands out of the way. There's a whole variety of these different types of safety circuits in pneumatic equipment that controls the overall function and designed to provide a safer environment for workers. This wraps up our conversation about fluid systems. As always, I recommend you read the text carefully and take advantage of the videos online and other materials. And as well, if you have any questions, do not hesitate to get in touch with me. Hopefully you had an enjoyable semester, and look forward to working with all of you again.